Hello dear friends, welcome to the lecture of real analysis. In this lecture we shall study multiple choice questions on metric spaces. Now to attempt a multiple choice questions on any topic, we must study the content, earlier content thoroughly. That means definition, examples, counter example, theorems, etc. Should be studied first, and we must understand the entire topic or content. Then we can attempt multiple choice questions on any topic. Only the thing is that we need not remember the entire proof of the theorems, but we must remember the at least statement of theorem, the meaning of it, and the other part also we have to understand. So we shall solve the MCQs on some of the MCQs on metric spaces. The questions I have written here, so I will pause a while. You should note all these questions and first solve yourself. Note down your answers, and then you can check it. So afterwards you can check it. First solve these yourself, and then you may check the answers. Now we shall attempt these questions. The first is a metric for m is a function row with domain m cross m, and range is contained in which of these following: A, B, C, D. So range is contained in minus infinity to infinity. We know that metric is a distance, and distance is necessarily non-negative. So therefore its range must be contained in non-negative real number set. And what is the non-negative real number set here is, it may be 0, but it should not be it must not be negative. So therefore this is not the choice here. It is 0 to infinity. So 0 is not included in this, and so this will not also be a choice. And again you see, this is negative. Minus infinity to 0 means negative real numbers, and only non-negative real numbers is the set C. And therefore by definition of metric, so this multiple choice question depends on the definition of metric, and therefore here the answer is this C. C is the answer. The second question is, if rho is a metric for set M, then rho is metric for any subset of M. That is first statement. Second statement is, rho is not a metric for any subset of M other than M. Then which of the following, which of these two statements is true? The alternatives are like this: only first is true, only second is true, both 1 and 2 are true, and both 1 and 2 are false. Now we see that if rho is a metric for any set M, then it is metric for any subset of M. The first is true. So if rho is a metric for R1, this set, then it is a metric for subset of R1, that means 0, 1. It will be also a metric for this set, subset of R1, and therefore the first statement is true. Now what about the second? Rho is not a metric for any subset. It is a negation of this other than M. So therefore second is not true, and that means only 1 is true. So this will be the correct alternative for the second question. The A is the correct alternative. Now the third question is, in any metric space, every convergent sequence is Cauchy. First statement. Second, every Cauchy sequence is convergent. And again similar type of alternatives are there. Only 1 is true. Now there are the results or theorem we have proved, as every convergent sequence is a Cauchy. For real numbers, every Cauchy will be also convergent, but it is not true for all metric, in any metric. So that means the first statement is true, every convergent sequence is Cauchy, but the second is not necessarily true. Every Cauchy sequence is convergent. This is not correct or not true, and therefore here also only first is true, only one is true. That is the answer. And now the fourth, which of the following is an open subset of an absolute value metric space R1? R1 with absolute value metric, and that metric space is given, and which subset is open. Now this is simple and straightforward. See, this is open interval 0 to 1, this is half open interval 0 to 1, this is singleton set 0, and we know that singleton sets are not open in R1, that are open in RD but not open in R1, and this is closed set, so these two are not there. This is not open because it is half open, and therefore the alternative will be A only. So this is the alternative, correct alternative. Now the fifth is, in discrete metric space RD, the open ball B, center with 0, radius 3 by 2 is equal to what? Now we have discussed this, so I shall rub this first question, two questions, so that we can do the rough work. For this, what is the definition of a discrete metric space? We know that the discrete metric is defined like this, D. So it is D of xy. D of xy is equal to 0. So this is equal to, this is 0 if x is equal to y, and this is 1 if x is not equal to y. So, and thus if x is not equal to y, then the distance between any two points is 1, different points is 1, and if x is equal to y, then the distance between x and y is 0. That means the open ball B around, so in discrete metric space, the open ball B around A of radius R, this is open ball. This will be containing only A if R is less than 1, and it will contain all of RD, all points, if R is greater than 1. So that is to be remembered, because if you consider the open ball with center A and the radius is 1, then there is no any other point except A inside this open ball. If R is less than 1 or less than or equal to 1, then so by definition we have to consider distance less than 1, and therefore it contains only one point, or here we can say R is less than or equal to 1. So if R is 1 also, then the open ball will be less than radius 1, and that will contain only single point. And if R is greater than 1 outside this, those points will be having distance. See, if x is not equal to 1, then the distance between x and y is equal to 1. So on the boundary of this open ball, all distinct points of RD are placed, and therefore if R is greater than 1, radius is greater than 1, then this is equal to RD. So the choice for this is A. RD is the correct answer for this. And if the question is like this, what will be B, open ball B, 0 or any other 1.5 in RD. So this will contain only 1 because the radius is less than 1. So therefore this will contain, this is equal to 1 only. So that is to be remembered for discrete metric spaces. Now next question is 6. Which of the following is not a closed subset of an absolute value metric space R1? Which is not a closed subset. Now what is the definition of closed set? It must contain all its limit points. And if you have a sequence of points in that set, the limit of that sequence must be in the set, then that set is closed. Now this is closed on 0 end, and that means this contains 0 and negative real numbers. So therefore this, if you consider any sequence of points in this set, then its limit will be again in the same set, and therefore this is closed. Singleton sets are always closed, so this is also closed, and this is of the same type. A is here, this end is closed, and infinity, that means all real numbers a less than or equal to x is less than infinity are there in this set, and this set also contains all its limit points, therefore it is closed. Only this is not closed. This is not closed, it is open, because it will not contain the point A. This set does not contain a point A. At the end, infinity always open. We should not write closed infinity to infinity. It is always written as minus infinity to plus infinity. If you write infinity, then that end is always open, because it is not a fixed number. So it is bigger and bigger, or smaller and smaller if negative sign is there. So therefore for infinity we should write the open parenthesis, and for 0 it is closed. So therefore it is a closed subset of R1. This is also closed, this is also closed, only this is not closed. So not closed, the answer is D. And seventh question, if B is the open interval 0 to 1, then the set of cluster points of B in R1 is, cluster point means limit points. The set of limit points of this interval will be the closed interval of this, that is the closure of this, and that will be the closed interval 0 to 1, that is direct. So therefore this is B. The correct alternative is B for seventh question. Now the eighth question is, if M row is R1, R1 is the metric space, and A is the set given as closed set 5 to 10. Then the open ball B 6, 3. What is A is here 5 to 10, that is given. So it is subset of R1, and we have to construct an open ball of radius 3 around 6. So what will be the meaning of this open ball B around 6 of radius 3? So that will mean the points which are at a distance 3 from 6, and therefore if you consider here the point as 6, 3 unit distance on the right side, that will give the point as say open end, that is 9, and 3 unit distance from left, that will give as 3. So those points x, which x belongs to A, such that row of x and A, that is A is 6, row of x and 6 is less than 3. This is the mean, and therefore distance from 6 is less than 3, so that is up to 9, and distance from 6 is less than 3 means it is 3. But that is those points in A. Now you see the points in A we have to consider, and A itself starts with 5, so it starts with 5, so 3 is not there, and it ends with 10. So the intersection of A and this set will be the open ball, and that means it will be actually 5 to 9, because 3 to 5 is not there. So this is actually the open interval 3 to 9. This is but it is in R1, so this is in R1, and in A it will be 5 to 9, and 5 will be closed end, because it is in A, and therefore it is closed at 5 and open at 9, and that is the correct alternative for this. You see, closed at 5, open at 9, the answer is C. So you should note it. Actually it is 3 to 9, but intersection with A becomes 5 to 9, and 5 is inside this or inside A, and therefore we have to take it 5 closed and 9 open. So that is the answer for 8. Now the next is 9th is, which of the following is connected subset of R1? Connected, we have seen this obviously is not connected, that is, it is disconnected in 1 to 1 2 and it is not connected. And if you take any 2 points in that set, then all in between points must be again in that set. That is roughly the meaning of connected set. And if you consider 1.5, then that is not here. So this is not connected. So discrete sets are not connected because it is 0 and half. In between points are not there. Only these are there. So this is not connected. It is similar to that. It is not connected. And this is connected because if you consider 0 to 1, then any point between 0 to 1, all the real numbers from 0 up to 1 are contained in this set, and therefore this set is connected. Earlier are not connected because here 1.5 or 1.5 is not there. Here between 1 by 4 is not there, and similarly here 1.5 is not there, and so the answer is D. So these are the correct alternatives for these questions. Now the question 10 is, if A is connected subset of the metric space M, so again I shall suggest you that you should observe these questions first. You should observe these questions first and solve it. Note your answers and then verify this. Now we shall see the 10th question. If A is connected subset of the metric space M, then closure of A is connected. The 2 statements are given. A is subset of B, B is subset of closure of B. That is always true. A set is subset of closure of the set. Then B is connected. If this is the second statement, then A, both first and second are 1 and 2 are correct. Only first is correct. Only second is correct. Both first and second are wrong. So what should be the case? If A is connected, then closure of A is connected. That is a result or an example. And therefore the first statement is true. Now what happens to the second? If A is subset of B, B is a subset of closure of B, then whether it implies B is connected. So for that purpose we can see this example. I shall consider the set A as say 0, 1, and we know this is subset of say -1, 2 union 3, 4, and this is subset of the closure of this -1, 2 union 3, 4. This will be B bar. This is B and this is B bar. So this happens here. A is subset of B, B is subset of the closure. Closure will be closed set. If B is open interval, then its closure is the closed set. And here obviously this relation is satisfied by A, B and B bar. But this B is not connected. B is connected is written here. B is not connected. It is contained, A is contained in this 0 to 1. That is obviously between minus in this interval -1 to 2. But it is union with 3, 4, and here is disconnection 2 to 3. The points between 2 and 3 are not in this set, and therefore this set is not connected, and that means this statement is false. That means only first is correct. So this is the answer. Now the next is 11. Consider the following statements. Open interval 0 to infinity is bounded subset of R1. Open interval 0 to infinity is not bounded subset of RD. And again the similar options are there, alternatives are there, which are correct. Both first and second are correct. Only first is correct, only second is correct, etc. Now we see 0 to infinity is bounded subset of R1. Is it right? and obviously this is not true, because distance between what is bounded, distance between any 2 points must be a finite number or less than a finite number m, then that set is said to be bounded, and this is not bounded. Obviously the distance cannot be less than m and fixed number, so therefore this statement is not true and not correct. And what about the second? 0 infinity is not bounded subset of RD. Not bounded. Now what is the distance between any 2 points in RD by definition of discrete metric space? We have d of xy is either 0 or 1. What about d of x and y? D of x and y is 0 if x is equal to y, and d of x and y is 1 if x is not equal to y. So that means there are only 2 distances in RD, either 0 or 1, and in any case 0 and 1 both are finite numbers, and that means distance remains finite in discrete metric space, and therefore this is bounded subset. Every subset of RD is always bounded, and here not is written, therefore this is also not correct. It is bounded, and therefore this statement is false or wrong. So thus that means both are wrong. So is the correct alternative for 11th. Now 12th. Which of the following is totally bounded subset of R1? So by definition of totally bounded subset of R1. So we know if R1 is considered, any finite subset of R1 is totally bounded. That is a result we have studied. And you see, finite subset we have to consider. This is not a finite, this is not finite, this is not finite. It is actually R1. And only the finite subset of R1 is this one, and therefore this is totally bounded. In R1, actually bounded and totally bounded are one and the same thing. So thus this is the right choice or correct alternative. 13th question is, if m row is metric space and T is a function from m to m is a contraction, that is a function we have defined, contraction on m, then the value of alpha belongs to R satisfying row of Tx and Ty. Distance between T of x and T of y is less than or equal to alpha times distance between x and y. That is the condition for the contraction. And what is the condition for alpha? That is asked for all x, y belongs to m, and alpha is the value of alpha is in the definition of contraction. And by the definition, the value of alpha, see, this distance is smaller than this distance, that we have to see. And when it will become smaller, if alpha is less than 1 and it lies between, it cannot be negative. So it must be between 0 and less than 1. So therefore the first alternative is 0 is strictly less than alpha is strictly less than 1, but the alpha may take the value 0, and therefore by definition this is the correct alternative. 0 is less than or equal to alpha is less than 1. So this is the condition for alpha. And 14th question is, which of the following is a complete subset of a discrete metric space RD? Complete. Complete means every sequence of points in that set must converge to the same set. Then that metric space we say as complete. See, in RD, the metric space is RD, and we know that every subset of RD is closed, and therefore here 0 1, the open interval 0 1, the open interval -1 1, and RD itself. So all these are complete, because if you consider a sequence in these, then that converges to RD itself, and therefore RD and all subsets of RD are complete. So that therefore here all of these are complete subsets of discrete metric space RD. If you consider R1, then it is not complete. So these two are not complete. So only the closed interval will be complete, but in RD it is complete. which of the following, 15th question is, which of the following is a compact subset of R1? Compact. Compact, the meaning it must be complete and totally bounded. So the 0, 1, and see this this is not complete, so it is not. And R1, it is not compact because it is not totally bounded. This is not totally bounded, it is infinite subset so of R1. R1 itself is infinite, so these two are not totally bounded, and this is not complete. So only this is complete and totally bounded, so therefore this is compact. Closed bounded intervals of R1 are compact, and therefore this is compact. Now the last or 16th question is, a metric space M is compact if it is. So this is direct definition. Compact if it is complete, connected, complete and totally bounded, totally bounded. So it must be complete and totally bounded. That is the very definition of compact metric space. So this is the right alternative for question number 16. So these are some MCQs that we have studied on metric spaces. Thank you.